Yo, what up? What up, what up, what up? We are here somewhere on Microtech. Checking if the stream is okay. Kinda looks like. We do a little bit different than usual. We do still do streaming, we do our commodity trading. We are, like we said, somewhere on Microtech. What we need to check is our fluid stuff. Do we have enough? We got some stuff around here. Water, empty. Should we trash? Bet we trash. What else do we have? More water. Interestingly, it says in the inventory, it says empty. And it is empty. The other one was empty as well, but for some reason it didn't show us. All right. Yeah, latency is worse today. All right, so what can we do? We are at SMO 10 and we can buy cobalt. We will do something like 10 of these. And the rest will be 8 ASUS. Yeah, almost empty. Nice. What we do different is we want to listen to a podcast or some audio files. Well, because Star Citizen is sci-fi, right? Science fiction. And we are here because we like science fiction. We love fiction about supposedly science, but there is more fiction than science in it. But at least we can believe as if the fiction is real, and that's why we're flying spacecrafts and flying around in a digital verse. Too many? Ah, god damn it. Can't we split fucking boxes? Nine, 10. What's on? God damn it. Yeah, it starts well, gotta say. Ship is still here, so as you can see, also based on the thumbnail, we got a lot of gray boxes inside this ship. And there's still some space. Yeah, there is an issue with the grid, as you can see. Yeah, there is still space in here. We can bring more boxes. This is not a particular low pop chart, but we haven't seen anybody around here because nobody comes here. Not that many come here. I mean, we had seen somebody bought, what was it, copper? No idea who is buying copper at an outpost like this. But maybe somebody read something on the what is the website called? UEX. When you read the numbers wrong, you think you can make plenty of profit if you do copper. It's the margin, it's the profit. You can rate the profit based on percentage or the pure going on, or the pure money per SCU. And this is what we do. We calculate the pure SCU per, no, the pure money per SCU. We do not mind if the margin is only something like 1%, because 1% of a box that costs you 100 money per SCU, that is 1000 profit per SCU. And usually we have lots of SCUs, as you can see, so that is lots of profit per SCUs there, because I mean it's still 1000 per SCU, but the what do we see? We have comments deactivated on YouTube. Since when that? Is that the reason why nobody's commenting? Comments on. Alright, we still have some space left. Should we? Nah, that's fine. So as you can see, most of the stuff here is off-grid. The only one gridded stuff is that stuff in the front part, and the rest is off-grid. Can we use the elevator? We should be able to use the elevator. Yes. That would be theft protection if you block the way from the ramp to the ladder. So that is a strategy you can go for to make sure nobody steals your ship here in Stanton. Because here in Stanton you cannot defend yourself. That is an issue. That's why we usually don't do trading here in Stanton. If a pirate shows up, he just needs to walk in and fly away. And we can't do anything about it or against it. The only thing that we can do is we could throw a box at him. So we go to Nick's first. Yeah, that is typical Star Citizen. You want to go to Nick's gateway instant, but the option you will get is Pyro. Stupid. This is, yeah, this is just stupid. And now... here we go.
Let me ask you something. What do you think light is? Go ahead, take your best guess. You probably said something like, light is energy that travels from one place to another. Or maybe light is tiny particles flying through space really, really fast. Or maybe you're a little more sophisticated and you said light is an electromagnetic wave rippling through the vacuum. Here's the thing. Every single one of those answers is wrong, or at least deeply, fundamentally incomplete in ways that should keep you up at night if you think about them carefully enough. I'm Leonard Susskind, and I have spent decades thinking about light. Decades. And I can tell you with complete honesty that light is one of the strangest things in the entire universe. Stranger than black holes. Stranger than the Big Bang. Stranger than quantum mechanics itself, in some ways, because light is the thing that connects all of those mysteries together. So buckle up, we're going to take apart everything you think you know about light, piece by piece, and put it back together in a way that's actually true. Let's start with the most basic misconception. Most people think light moves. They think it travels, that it goes from here to there, that it takes time to make the journey, and on the surface, that seems obviously correct. Light from the sun takes about 8 minutes to reach the Earth. Light from distant stars takes years, even millions of years. So clearly, light is moving, right? Except from the perspective of the light itself, none of that is true. Not even a little bit. Here's what I mean. In Einstein's special relativity, there's this concept called proper time. Proper time is the time experienced by an object as it moves through space-time. For you and me, proper time ticks away steadily. We age. We experience the passage of time. We have memories of the past and anticipation of the future. Our proper time is real and measurable. Now, a photon, a single particle of light, has zero proper time. Zero. None. The photon that left the surface of the sun 8 minutes ago, from its own perspective, arrived at your eye at exactly the same moment it was emitted. No time passed. No journey occurred. The emission and the absorption are, from the photon's point of view, the same event. Think about that for a second. You look up at the sun, and the light hitting your face has been traveling for 8 minutes by your clock, but for that light, there was no traveling. There was no 8 minutes. There was nothing in between. The sun and your eye are, from the photon's perspective, the same place at the same time. And it gets even more mind-bending than that. The light from the Andromeda galaxy that's 2.5 million light years away, it's been traveling through space for 2.5 million years by our reckoning. But for that photon, for that single particle of light, no time has passed. None. It's the same as if Andromeda were right next to us. From the photon's perspective, there is no distance either. The light doesn't experience space or time during its journey because there is no journey. Now, I know what you're thinking. Lenny, that's crazy. How can something travel 2.5 million light years and not experience any time? That doesn't make sense. And you're right, it doesn't make sense. Not to our intuitions anyway, but our intuitions evolved to deal with speeds much, much slower than light. We evolved to navigate a world where things take time to get from here to there. The universe doesn't care about our intuitions. It does what the mathematics tells it to do, and the mathematics is absolutely clear on this point. Photons don't experience time. This leads to a fascinating philosophical question. Does light actually move at all? In one sense, yes, we observe it, we measure its speed, we know it takes finite time to cross distances, as measured by our clocks. But in another sense, no, from the photon's own frame of reference, there is no motion, no passage of time, no journey. It simply is existing at both endpoints simultaneously. This is not just some abstract philosophical puzzle. This is a direct consequence of Einstein's special relativity, one of the most thoroughly tested theories in all of physics. We've confirmed time dilation, the slowing of clocks for moving objects thousands upon thousands of times in particle accelerators, with GPS satellites, with cosmic ray measurements. It's a fact of nature. Now let's talk about something that confuses almost everyone: the speed of light. Everyone knows that light travels at about 300,000 kilometers per second. That's the cosmic speed limit. Nothing can go faster. Einstein said so, and he was right. Except, and this is where people get really confused, that's only true in a vacuum. In a vacuum, light travels at exactly 299,792,458 meters per second. That number is so important that we've actually defined the meter in terms of it. The meter is now officially defined as the distance light travels in 1/299,792,458 of a second. So in a very real sense, the speed of light defines our unit of length. But when light enters a medium, water, glass, air, anything, it slows down, dramatically in some cases. In water, light travels at about 75% of its vacuum speed. In glass, it can be even slower. In some exotic materials, physicists have slowed light down to a crawl, literally walking speed. In 1999, a team at Harvard actually brought light to a near-complete stop inside a cloud of ultra-cold atoms, 17 meters per second. You could outrun it on a bicycle. And here's the really weird part. In 2013, physicists actually stopped light completely. They stored it inside a crystal for a full minute and then released it. Light frozen in place like a fly in amber. So what's going on? How can light, the fastest thing in the universe, be stopped dead in its tracks? The answer is that individual photons, the actual particles of light, never slow down. They always travel at c, the speed of light in a vacuum. What happens when light enters a medium is much more subtle and much more interesting than simple slowing down. When light enters, say, a piece of glass, the photons interact with the atoms in the glass. They get absorbed by the electrons in those atoms, and then almost instantaneously, the atoms re-emit new photons. These new photons travel at c between atoms, but there's a tiny delay, a tiny pause between absorption and re-emission. And it's these tiny delays, accumulated over billions of interactions, that make light appear to slow down. So the light isn't actually moving slower. The individual photons are still zipping along at 300,000 kilometers per second between each atom. But the overall propagation of the light signal, the information being carried, is slower because of all those little stops and starts. It's like driving on a highway with lots of traffic lights. Your car might be going 100 kilometers per hour between each light, but your average speed over the whole trip is much lower because of all the stopping. The light is doing the same thing. It's not that it's moving slower, it's that it's being interrupted constantly. And this distinction matters enormously because it means that even when light is slowed down in a medium, nothing has actually violated the speed limit. The photons are still traveling at c between interactions. The cosmic speed limit is never broken. But here's where it gets really interesting and a little bit controversial. If light slows down in a medium, that means other particles can potentially go faster than light in that medium. And when they do, something spectacular happens. It's called Cherenkov radiation, and it's the optical equivalent of a sonic boom. You know what a sonic boom is, right? When an airplane breaks the sound barrier, when it goes faster than the speed of sound in air, it creates a shock wave. A boom. Well, when a charged particle, usually an electron, travels through a medium faster than light travels through that same medium, it creates a similar shock wave, but made of light. A cone of blue light radiating outward from the particle's path. This isn't science fiction. This is real observed physics. You can see Cherenkov radiation in nuclear reactors, that distinctive blue glow in the cooling water around the fuel rods. It's beautiful, and it's deeply weird, because you're watching something go faster than light. Now, before you get too excited about building a faster than light spaceship, let me be very clear. Nothing in this scenario is actually exceeding the fundamental speed limit. The cosmic speed limit is c, the speed of light in a vacuum, not the speed of light in water. The electrons producing Cherenkov radiation are going faster than light in water, but they're still going slower than light in a vacuum. The speed limit hasn't been broken. The universe is still consistent. But this raises a fascinating question. Is there anything that could actually go faster than c, faster than light in a vacuum? Theoretically, some physicists have proposed the existence of hypothetical particles called tachyons. Tachyons would be particles that always travel faster than light. They couldn't slow down to the speed of light any more than we could speed up to it. For tachyons, the speed of light would be a lower bound rather than an upper bound. The mathematics of tachyons is interesting, but deeply problematic. If tachyons exist, they would have imaginary mass, and I mean that in the mathematical sense, not the colloquial sense, the square root of a negative number. And even more disturbing, tachyons could potentially allow information to travel backward in time, which would violate causality in a very fundamental way. Most physicists today regard tachyons as a mathematical curiosity rather than a real physical entity. We've never observed one, and there are good theoretical reasons to think they don't exist. But the fact that the equations allow for them tells us something interesting about the structure of space-time and the nature of the speed limit. Now let's talk about one of the deepest and most fundamental questions about light. What exactly is it? You might think this is a simple question. Light is electromagnetic radiation. It's made up of photons. It has both wave properties and particle properties. Wave-particle duality, you've probably heard of it. It's one of those things that every physics student learns about. But wave-particle duality is actually a much deeper and stranger concept than most people realize. Let me walk you through why. In the 1600s, there was a famous debate about the nature of light. Isaac Newton argued that light was made up of tiny particles, corpuscles, he called them. Christian Huygens argued that light was a wave propagating through some medium. For about 200 years, Newton's particle picture won. Light was particles. End of story. Then in the 1800s, a series of experiments, Young's double-slit experiment being the most famous, showed conclusively that light behaves like a wave. It interferes with itself, it diffracts around obstacles, it does all the things waves do. So the scientific consensus shifted. Light is a wave. But then in the early 1900s, along came Albert Einstein, and he turned everything upside down again. In 1905, the same year he published Special Relativity, Einstein explained the photoelectric effect. The photoelectric effect is when you shine light on a metal surface and electrons pop off. Classical wave theory couldn't explain some of the details of this effect. Specifically, it couldn't explain why the energy of the ejected electrons depended on the frequency of the light and not on its intensity. If light were purely a wave, brighter light should produce higher energy electrons, but it didn't. Only higher frequency light produced higher energy electrons regardless of brightness. Einstein's explanation was radical. Light comes in discrete packets of energy, which he called quanta. Each quantum has an energy proportional to its frequency. These quanta are what we now call photons. And this explanation perfectly accounted for the photoelectric effect. So now we had a problem. Light behaved like a wave in some experiments and like a particle in others. How could it be both? The answer that quantum mechanics eventually gave us is both profound and deeply unsatisfying. Light is neither a wave nor a particle. It's something else entirely, something for which we don't have a good word in everyday language. It's a quantum object, and quantum objects don't behave like anything in our everyday experience. When you set up an experiment that's sensitive to wave properties, like Young's double-slit experiment, light behaves like a wave. When you set up an experiment that's sensitive to particle properties, like the photoelectric effect, light behaves like a particle. The light doesn't choose which one to be. The experiment determines which aspect of its nature gets revealed. And here's the really mind-bending part. If you do the double-slit experiment with single photons, one photon at a time, you still get an interference pattern. One photon at a time, and you still get waves interfering with each other. How can a single particle interfere with itself? The answer is that the photon doesn't go through one slit or the other. In some sense, it goes through both. Its quantum state, described by what we call the wave function, passes through both slits simultaneously and interferes with itself on the other side. Only when you detect the photon on the screen does it collapse to a definite position. This is one of the strangest facts in all of physics, and after nearly 100 years of quantum mechanics, we still don't fully understand what it means. But it's been confirmed by experiment thousands of times. It's not a matter of interpretation, it's a fact. Now, let me talk about something even stranger, something that Einstein himself called spooky action at a distance, and something that has profound implications for how light and information can and cannot travel through the universe. It's called quantum entanglement, and it's the weirdest thing in physics. Here's the basic idea. You can create pairs of photons that are entangled, linked together in a quantum mechanical way. When you create these pairs, their properties are correlated. If you measure the polarization of one photon and find it's vertical, the other photon will always be horizontal, no matter how far apart they are. Now, here's the spooky part. Before you measure either photon, neither one has a definite polarization. They're both in a superposition of vertical and horizontal. The polarization only becomes definite at the moment of measurement. And when it becomes definite for one photon, it instantly becomes definite for the other, even if the other photon is on the other side of the universe. Einstein hated this. He thought it proved that quantum mechanics was incomplete, that there must be some hidden information, some pre-existing property that determines the outcome of the measurement before it happens. He called this idea local hidden variables. But in 1964, a physicist named John Bell showed that you could actually design experiments to test whether local hidden variables exist. Bell devised a set of mathematical inequalities, Bell inequalities, that any local hidden variable theory must satisfy. If quantum mechanics was right, and the correlations were really instantaneous, the Bell inequalities would be violated. And when the experiments were done starting in the 1980s with Elaine Aspect's famous experiments, and continuing right up to the present day, the Bell inequalities were violated every single time. Quantum mechanics was right. Local hidden variables don't exist. The correlations are real, and they are instantaneous. So does this mean information can travel faster than light? Can we use entanglement to send messages instantaneously across the universe? No. And this is a crucial point. Entanglement cannot be used to transmit information. When you measure your photon, you get a random result, vertical or horizontal, with equal probability. You can't control what result you get. And because you can't control it, you can't encode a message in it, the correlations between the two photons only become apparent when you compare your results, and that comparison has to happen through ordinary, slower than light communication. So Entanglement is spooky, but it doesn't break the speed of light. The universe is cleverly designed, if you can even use that word, to prevent faster-than-light information transfer, even in the face of instantaneous quantum correlations. This is one of the things I find most beautiful about physics. There's this deep consistency to the universe. The different pieces of the puzzle, relativity, quantum mechanics, information theory, they all fit together in a way that's incredibly tight. The speed of light is protected. Causality is protected. No matter how clever you are, no matter how hard you try, you cannot send information faster than light. The universe won't let you. Now, let me talk about something that might seem like a tangent, but is actually deeply connected to everything we've discussed. The electromagnetic spectrum. When most people think about light, they think about visible light, the narrow band of electromagnetic radiation that our eyes can detect. Red, orange, yellow, green, blue, violet. That's it. That's all we see. But visible light is a tiny, tiny fraction of the electromagnetic spectrum. A ridiculously tiny fraction. The electromagnetic spectrum extends from radio waves with wavelengths of meters or even kilometers, all the way up to gamma rays with wavelengths smaller than an atom. And here's the thing. All of these are light. Radio waves are light. Microwaves are light. Infrared is light. Ultraviolet is light. X-rays are light. Gamma rays are light. They're all the same thing. Electromagnetic radiation, photons, just at different frequencies and wavelengths. The only difference between a radio wave and a gamma ray is energy. A gamma ray photon has enormously more energy than a radio wave photon. But they're both photons. They both travel at sea in a vacuum. They both have wave-particle duality. They both obey the same laws of physics. So when you use your microwave oven to heat your food, you're literally bombarding it with light. When your radio picks up a signal from a radio station, it's detecting light. When you get an X-ray at the dentist is shining light through your teeth. It's all light. This unified picture, the idea that all electromagnetic phenomena are manifestations of a single force carried by a single type of particle, the photon is one of the great intellectual achievements of physics. It was first understood by James Clerk Maxwell in the 1860s when he unified electricity and magnetism into a single theory. Maxwell showed that changing electric fields create magnetic fields, and changing magnetic fields create electric fields, and these two fields can leapfrog each other through empty space, propagating as a wave. And when he calculated the speed of this wave, he got exactly the speed of light. That was a stunning discovery. Maxwell didn't know he was going to get the speed of light. He was just doing the math, following the equations where they led. And out popped the speed of light, perfectly matching the measured value. That was the moment when physicists realized that light is electromagnetic radiation. But even Maxwell didn't fully understand what was going on. It took Einstein 50 years later to really grasp the deep significance of the speed of light. Einstein realized that the speed of light isn't just the speed of electromagnetic waves, it's the speed of causality itself. It's the fundamental speed limit of the universe, built into the structure of space-time, and that's why c, the speed of light, shows up in relativity. Not because Einstein was thinking about light specifically, but because he was thinking about the structure of space-time. The speed of light is the conversion factor between space and time. It's what links the two into a single unified space-time. In fact, some physicists argue that we should stop calling it the speed of light altogether, because that phrase implies it's a property of light specifically. It's not. It's a property of space-time. Light just happens to travel at that speed because photons are massless. If photons had mass, even a tiny, tiny mass, they would travel slower than c, but c would still be c. The speed limit would still be there. Let me get into something really speculative now, because I think it's one of the most fascinating questions about light in the universe. Why does light travel at the speed it does? Why is c what it is? Why 300,000 kilometers per second and not some other number? This is a surprisingly deep question, and the answer is subtle. In one sense, the numerical value of c doesn't matter. It depends on your units. In meters per second, it's about 300 million. In miles per second, it's about 186,000. In light years per year, it's exactly 1. The number changes depending on how you define your units of length and time. What matters is the dimensionless constants of nature numbers that don't depend on units. One of the most important of these is the fine structure constant, usually denoted by the Greek letter alpha. It's a number that involves the speed of light, Planck's constant, and the charge of the electron, all combined in such a way that the units cancel out, and its value is approximately 1 over 137. The fine structure constant determines the strength of the electromagnetic force. It determines how strongly light interacts with matter. It determines the structure of atoms, the colors of stars, the chemistry of the universe. Why is it 1 over 137? We have no idea. It's one of the great mysteries of physics. If it was significantly different, say 1 over 100 or 1 over 200, the universe would look completely different. Atoms might not be stable. Stars might not shine the way they do. Life as we know it might be impossible. This is what physicists call the fine-tuning problem, and it connects to deep questions about why the universe has the physical constants it has. Some physicists think there might be a deeper theory that explains these constants from first principles. Others think we might just be one universe among many part of a vast multiverse, and we happen to live in one where the constants are just right for complexity and life. I've gone back and forth on this over my career. I was one of the people who developed the string theory landscape, the idea that there are an astronomical number of possible universes with different physical constants. It's controversial, and not everyone agrees with it, but it does suggest that the value of the speed of light and all the other constants might not be as mysterious as we think if there are enough universes to try every possible combination. But regardless of whether the multiverse is real, the fact remains. In our universe, light travels at exactly 299,792,458 meters per second in a vacuum. It's one of the most precisely known numbers in all of science, and it's one of the most important. Let me bring this back to something personal. When I was younger, long before I became a physicist, I used to look up at the night sky and wonder about the stars. I had no idea at all that the light hitting my eyes from those stars was carrying information about the past, that I was literally looking backward in time every time I looked at the sky. Now I understand that, and it still takes my breath away. The light from Betelgeuse, that reddish star in Orion, has been traveling for about 700 years before it reaches your eye. You're seeing that star as it was 700 years ago. It might have changed dramatically since then. For all we know, it might have exploded into a supernova already, and we just haven't seen it yet because the light from that explosion hasn't reached us. Light is our only messenger from the distant universe. Everything we know about what's out there, every galaxy, every star, every nebula, we know because of light that traveled from there to here. And every one of those photons, every single one, experienced 0 time during its journey. There's something profoundly poetic about that, even though I'm a physicist and I usually try to keep poetry out of my work. These photons, these tiny packets of energy, zip across the cosmos in what amounts to an instant from their own perspective, carrying the light and information of entire civilizations of stars, entire histories of galaxies. And they do it without experiencing a single moment of time. Light doesn't move in the deepest sense. It connects points in space-time, but it doesn't experience the journey between them. It's more like a bridge than a vehicle. A bridge between the past and the present, between distant stars and your own eyes, between the beginning of the universe and right now. That's what light really is. Not a wave, not a particle, not an electromagnetic disturbance. It's a connection. A thread woven into the fabric of space-time itself, linking events that might be separated by millions of light years and millions of years, but are, from the photon's perspective, one and the same. And that, to me, is far more beautiful and far more profound than anything science fiction has ever imagined about light and speed and the cosmos. Let me wrap this up by coming back to the beginning. You thought light moves. You thought it travels from one place to another, taking time to make the journey. And in the sense, in the sense of what we observe with our instruments and our clocks, that's true. Light does take 8 minutes to get from the sun to the earth. It does take years to cross interstellar distances. But in the deeper sense, in the sense of what's really happening in the structure of space-time, light doesn't move at all. It doesn't experience time. It doesn't experience distance. It exists at both endpoints simultaneously. The journey is an illusion, a consequence of how we experience space-time, not a feature of how light experiences it. And there's more. Light isn't just one thing. It's a whole spectrum, from radio waves to gamma rays, all unified by the same physics. It can be slowed down, stopped, even frozen, without violating any fundamental law. It can be entangled with other light across cosmic distances, exhibiting correlations that are instantaneous but can never be used to send information faster than the speed of light. Light is weird. Light is deeply, fundamentally weird, and after 50 years of studying it, I can tell you that we still don't fully understand it. There are still open questions, still mysteries, still things that keep physicists up at night.
Yeah, we would have.
But here's what I love about it. The more we learn about light, the more connected everything becomes. Light connects electromagnetism to space-time. Light connects the quantum world to the classical world. Light connects the past to the present. Light is, in a very real sense, the glue that holds our understanding of the universe together. So the next time you look at the sun, or see a rainbow, or turn on a lamp, remember, what you're experiencing is not what you think it is. What you're experiencing is one of the most profound and mysterious phenomena in the entire universe, and we're only just beginning to understand it. That's what makes physics exciting. That's what makes light exciting. After all these centuries, after all we've learned, the universe can still surprise us with the simplest things. Light doesn't move the way you think, and that's a beautiful, wonderful, magnificent fact. Thank you for listening. Now go look at the sky and think about all the photons hitting your face right now that have been traveling for years, centuries, millennia, and experiencing not a single second of it. Think about that. Really think about it. And welcome to the real universe.
The universe. The verse, one line. Uni, one verse, line. It's all a fiction. It's all a fiction.
Let me start by saying something that might surprise you. I am not an aerospace engineer. I'm a theoretical physicist. I spend my time thinking about black holes, quantum mechanics, string theory, not rocket ships and space missions. So why am I making a video about Mars? Because there are fundamental physics problems with sending humans to Mars that go way beyond engineering challenges. Problems that aren't about building better rockets or designing better spacesuits. Problems that are rooted in the basic laws of nature thermodynamics, nuclear physics, radiation biology, and these problems, I think, are far more serious than most people realize. I'm Leonard Susskind, and I want to talk about why we will probably never send humans to Mars. Not because it's impossible in principle, but because the physics of the problem, the actual fundamental physics, makes it so difficult, so dangerous, and so expensive that I don't think we'll ever do it. At least not in any time frame that matters. Now, I know what you're thinking, but Lenny, we've sent rovers to Mars. We've landed spacecraft on Mars. We've studied Mars from orbit for decades. How can you say we'll never go there? And you're right, we've done all those things. With robots, with machines that don't need food, water, oxygen, or protection from radiation. Machines that don't care if the trip takes 9 months. Machines that don't have families waiting for them at home. Machines that we can afford to lose if something goes wrong. Sending humans is a completely different problem, and the physics of that problem is what I want to talk about. Let's start with the most fundamental barrier, radiation. Space is filled with radiation, high-energy particles traveling at nearly the speed of light, slamming into everything in their path. On Earth, we're protected from this radiation by two things, our atmosphere and our magnetic field. The atmosphere absorbs and scatters the particles. The magnetic field deflects charged particles, channeling them toward the poles where they create the aurora but don't reach the ground. Mars has neither. Mars has almost no magnetic field. It lost its global magnetic field billions of years ago. And Mars has almost no atmosphere. The atmospheric pressure on Mars is about 1% of Earth's. So if you're on the surface of Mars, you're exposed to cosmic radiation with almost no shielding. But it gets worse. To get to Mars, you have to spend months in space traveling through the interplanetary radiation environment with no protection at all except whatever shielding your spacecraft provides. Let me give you some numbers because the numbers are truly shocking. On Earth, the average person receives about 2.4 millisieverts of radiation per year from natural sources. That's background radiation from cosmic rays, radon in the air, potassium 40 inches your body, everything combined. 2.4 millisieverts per year. On a trip to Mars, a round trip, let's say 30 months total, you would receive somewhere between 300 and 600 millisieverts. That's 125 to 250 times the normal annual dose, compressed into 2.5 years. And that's assuming you don't encounter any solar particle events, massive bursts of radiation from solar flares that can deliver lethal doses in hours if you're not properly shielded. Now, here's where the physics gets really ugly. The radiation you're exposed to in space is not like the radiation you get from a medical X-ray or even from a nuclear accident. It's qualitatively different, more dangerous, more damaging to biological tissue. The radiation in space includes something called HZE particles, high charge, high energy nuclei. These are the nuclei of heavy elements like iron, traveling at close to the speed of light. When one of these particles passes through your body, it doesn't just damage a few cells. It creates a track of destruction, a line of completely destroyed cells, DNA shredded beyond repair, proteins denatured, membranes ruptured. And here's the problem. We don't actually know how dangerous this is. Not precisely, because we've never exposed humans to this kind of radiation for extended periods. The astronauts on the International Space Station are still protected by Earth's magnetic field. They're in low Earth orbit, inside the magnetosphere. They get higher doses than people on the ground, but nothing like what you get on a Mars mission.
Inside
the few astronauts who have left Earth orbit, the Apollo astronauts who went to the moon, were only in the interplanetary environment for a few days, not months, not years. And even then, Some of them have shown elevated rates of cardiovascular disease later in life, possibly linked to their radiation exposure. So when we estimate the cancer risk, the cardiovascular risk, the neurological damage risk from a Mars mission, we're extrapolating way beyond our data. We're guessing. Educated guessing, but guessing nonetheless. And the guesses are not encouraging. NASA's own risk assessment suggests that a Mars mission would give astronauts a lifetime cancer risk increase of somewhere between 5 and 20%. 5 to 20%. That's enormous. For comparison, smoking a pack of cigarettes a day for 40 years increases your cancer risk by about 10 to 15%. So we're talking about exposing people to a cancer risk equivalent to a lifetime of heavy smoking just from the radiation exposure on a single Mars mission. Now, you might say, okay, so we shield the spacecraft. We use thick walls, water tanks, whatever it takes to block the radiation. And yes, shielding helps, but here's the problem. Shielding is heavy, really heavy, and the amount of shielding you'd need to significantly reduce the radiation dose is impractical with any foreseeable rocket technology. To give you a sense of scale, to reduce the radiation dose by a factor of 2, you need several centimeters of aluminum or several meters of water surrounding the entire habitable volume. And to get down to something approaching safe levels, comparable to what astronauts on the ISS experience, you'd need even more. This is a fundamental problem of physics.
Total
the radiation is high energy. High energy particles penetrate matter. To stop them, you need mass, lots of mass. And mass is exactly what you don't want when you're trying to launch something into space and fly it to another planet. There's actually an even more insidious problem with shielding. When high energy particles hit shielding material, they can create secondary radiation showers of neutrons and other particles that are themselves dangerous. So adding more shielding can, in some cases, actually make the radiation problem worse, not better. This is not an engineering problem. This is a fundamental physics problem. The cross-sections for nuclear interactions, the energies involved, the production of secondary particles, these are determined by the laws of nuclear physics, and there's nothing we can do to change them. Now let me talk about the second fundamental barrier, energy and propulsion. To get to Mars, you need to accelerate a very large mass, the spacecraft, the fuel, the life support systems, the crew, the supplies, to a very high velocity. And then, when you get to Mars, you need to decelerate. And then, when you want to come home, you need to accelerate again and decelerate again when you reach Earth. The amount of energy required for this is staggering. And the problem is the rocket equation, a simple consequence of Newton's laws and the conservation of momentum. The rocket equation tells you that the mass ratio, the ratio of the fully fueled rocket to the empty rocket, grows exponentially with the change in velocity you want to achieve. If you want to go faster, or if you want to carry more payload, you need exponentially more fuel. And here's the killer. You have to carry all that fuel with you. Every kilogram of payload requires many kilograms of fuel, but that fuel also has mass. So you need fuel to carry the fuel, and fuel to carry the fuel to carry the fuel. It compounds. For a Mars mission, the mass ratio is enormous. You might launch with 10 or 20 times more mass in fuel than in actual payload and structure. And that's using chemical rockets, the best chemical propulsion we have. Could we do better? In principle, yes. Nuclear rockets, ion drives, various other advanced propulsion concepts could improve the situation. But these technologies have their own problems. Nuclear rockets involve launching nuclear reactors into space, with all the political and safety concerns that entails. Ion drives produce very low thrust. They can run for months or years, but they can't get you off the ground. You need something else for the initial launch. And fundamentally, all of these are still limited by thermodynamics. You can't create energy from nothing. You have to carry your energy source with you, whether it's chemical fuel, nuclear fuel, or solar panels and electrical power. And the laws of thermodynamics put hard limits on how efficiently you can convert that energy into kinetic energy of the spacecraft. These aren't engineering challenges. These are fundamental limits imposed by the laws of physics. Now, let me talk about the third barrier, which is one that people don't think about as much, but which I think is actually the most serious. The human body is not designed for space. We evolved in Earth's gravity, 1G. Our cardiovascular system, our musculoskeletal system, our vestibular system, our immune system, all of them are tuned to operate in 1G of gravitational acceleration. In microgravity, the condition you experience in orbit or during spaceflight, everything goes wrong. Your bones lose density, your muscles atrophy. Your cardiovascular system weakens because it doesn't have to work as hard to pump blood. Your immune system becomes compromised. Fluids shift toward your head, causing vision problems that can be permanent. We know this from decades of experience on the International Space Station. Astronauts who spend 6 months on the ISS lose 1 to 2% of their bone density per month. Their muscles weaken significantly, even with hours of exercise every day. Some of them develop vision problems that don't fully reverse when they return to Earth. Now imagine a Mars mission. Not 6 months. 2.5 years, 9 months to get there, 18 months on Mars at 1/3 G, which is better than 0G, but still not enough to prevent degradation. 9 months to get back. By the time you return to Earth, your bones will be osteoporotic, your muscles will be severely weakened, your heart will struggle to pump blood against Earth's gravity, you might have permanent vision damage, your immune system will be shot. Could you survive? Probably. With intensive medical support, physical therapy, long-term treatment, but you would not be healthy. And there's a real possibility that some of the damage would be irreversible. And here's the really disturbing part. We don't know if the human body can even survive the trip at all. We've never sent humans beyond low Earth orbit for more than a few days. We don't know what happens to the body after months or years in deep space, exposed to cosmic radiation and microgravity simultaneously. There might be synergistic effects. The radiation might make the bone loss worse, or the muscle atrophy might make you more vulnerable to radiation damage. We simply don't know. This is not an engineering problem. This is a biology problem. And biology, unlike engineering, can't always be solved with better technology. Now let me talk about cost, because cost is where all of these physics problems come together and become insurmountable. NASA estimates that a human mission to Mars would cost somewhere between $500 billion and $1 trillion, half a trillion to $1 trillion. For comparison, the entire Apollo program, all the missions, all the infrastructure, all the development, cost about $200 billion in today's dollars. And that was to go to the moon, which is 3 days away, not 9 months. Mars is vastly more difficult. You can't abort and come home if something goes wrong. The orbital mechanics don't allow it. You can't send a rescue mission. By the time it arrived, the crew would be dead. You need redundant systems for everything. Life support that can run for years without resupply, radiation shielding, medical facilities, habitats on the Martian surface, return vehicles, fuel production on Mars because you can't carry enough fuel for the return trip. All of this mass has to be launched from Earth. And launching mass to space is expensive. Even with reusable rockets, even with the most optimistic cost projections, we're talking about hundreds of billions of dollars just for the launch costs. And for what? What do we get for $500 billion? We get to say we sent humans to Mars. We get some scientific data, though honestly, robots can collect most of that data for a tiny fraction of the cost. We get to wave flags and take selfies. Is it worth it? From a pure science perspective, absolutely not. Robots are cheaper, safer, and can stay on Mars indefinitely. From a pure exploration perspective, maybe, but only if you value human exploration for its own sake, regardless of the cost. And here's the thing. I don't think society will be willing to pay that cost, not when there are so many other problems to solve here on Earth. climate change,
highly
poverty,
doubt that
disease,
they want to spend money for all
infrastructure.
those.
You could do an enormous amount of good with $500 billion spent on Earth. Now, I know the counter-argument. People say that space exploration inspires us, pushes technology forward, gives us a sense of purpose. And that's all true. Apollo inspired a generation. The pictures of Earth from space changed how we think about our planet. But Mars is not the moon. The moon is 3 days away. You can watch the astronauts live on TV. You can communicate with them in real time. If something goes wrong, you have a chance, a slim chance, but a chance to bring them home. Mars is 9 months away. Communication has a 20-minute round-trip delay. If something goes catastrophic, there is absolutely nothing we can do. The astronauts are on their own, and unlike the moon, where you can survive on the surface in a spacesuit for a few hours, on Mars you'd last maybe a minute before the low pressure and radiation killed you. The risk is enormous, the cost is enormous, and the benefit, the actual tangible benefit beyond national prestige, is unclear. I think that's why we haven't gone to Mars yet, and why we probably never will. Not because it's impossible, but because when you actually run the numbers, when you actually confront the physics of the problem, it doesn't make sense. Now, could I be wrong? Of course. Maybe someone will develop a revolutionary new propulsion technology. Maybe we'll discover a way to shield against cosmic radiation that doesn't require tons of mass. Maybe we'll figure out how to keep the human body healthy in microgravity for years. Maybe the cost will come down by an order of magnitude. But I've been around long enough to be skeptical of revolutionary breakthroughs. In physics, we make progress incrementally. We understand the limits imposed by the laws of nature, and those limits are hard. You can't cheat thermodynamics. You can't cheat the rocket equation. You can't cheat nuclear physics. And even if we solve all the technical problems, we still have the economic problem. Who's going to pay for it? Governments? Governments can barely fund basic science research. They're not going to spend $500 billion on a Mars mission when they have budgets to balance and voters to please. Private companies? Maybe. SpaceX has ambitious plans, but Elon Musk's estimates of cost and timeline have consistently been optimistic, shall we say. And even if SpaceX succeeds in dramatically lowering launch costs, the other costs, life support, radiation shielding, habitats, medical systems, don't go away. You know, when I was younger, I used to dream about space exploration. I thought for sure we'd have moon bases by now, Mars colonies, O'Neill cylinders, the works. But the more I've learned about physics, the more I've come to appreciate just how hostile space is. Space is not the final frontier in the way that the American West was the frontier. The American West was hard, but it was fundamentally habitable. You could breathe the air, you could drink the water. You could grow crops, you could live there without massive technological support. Space is not like that. Space is an incredibly hostile environment that actively tries to kill you every second you're there. And Mars, while better than the vacuum of space, is still fundamentally hostile. Unbreathable atmosphere, lethal radiation, freezing temperatures, toxic soil, no liquid water. Making Mars habitable, really habitable, not just survivable for a few months in a tin can, would require terraforming on a scale that makes every engineering project in human history look trivial by comparison. We're talking about giving Mars a magnetosphere, thickening its atmosphere by orders of magnitude, warming it by dozens of degrees, making the soil fertile. This would take thousands of years, minimum, maybe millions. And the energy requirements would be astronomical. So when people talk about becoming a multiplanetary species, I think they're vastly underestimating what that would actually require. We're not going to colonize Mars the way Europeans colonized the Americas. The physics doesn't allow it. Does this mean we should stop exploring Mars? Absolutely not. We should send more robots, better robots. Robots that can drill deep into the Martian crust, analyze the geology, search for signs of past or present life. We should study Mars intensively because it's fascinating and because it tells us about the history of our own planet. But humans? I don't think so. I think the risks are too high, the costs are too high, and the benefits are too uncertain. And I say this as someone who loves physics, who loves the idea of exploration, who would be thrilled to be proven wrong. I would love to see humans on Mars in my lifetime. I just don't think it's going to happen. Not because we lack the will or the imagination, but because the laws of physics are what they are, and they make the problem extraordinarily difficult. Maybe future generations will find a way. Maybe in 100 years or 200 years, technology will have advanced to the point where a Mars mission is routine and affordable. Maybe they'll look back at this video and laugh at how pessimistic I was. But based on what we know now, based on the physics as we understand it, I think we will never reach Mars. Not never in the absolute sense, but never in any practical, sustainable way that makes sense given the costs and the risks. The universe is vast and beautiful and full of wonders, but it is also incredibly hostile to life. Earth is our home, and it's the only home we're likely to have for a very, very long time. Thank you for listening. I hope I'm wrong, but I don't think I am.
We are heading to Battlefield, buying some boxes. And then afterwards we will go to Sacrin's plot, because that is on Pyro 4 as well. And afterwards Ashland, but I don't think that we can buy actually good commodities at Ashland. The only one thing that we know of is a Miyoshi Plague, but usually it's kinda out of stock. So next thing will be why intelligent life is unlikely.
I'm going to make an argument that will sound pessimistic, maybe even depressing, but I think it's probably correct based on what we know about physics, biology, and the universe. Intelligent life is unlikely. Extraordinarily, improbably, astonishingly unlikely. We might be alone in the galaxy. We might even be alone in the observable universe. And the silence we hear when we listen for alien signals, the deafening cosmic silence, might not be because we're looking in the wrong way or listening on the wrong frequencies. It might be because there's simply nobody out there. I'm Leonard Susskind, and I've spent my career thinking about the universe on the largest and smallest scales. And the more I learn, the more I appreciate just how special, how contingent, how fragile the emergence of intelligent life really is. Let me start with the Fermi paradox, because that's where this whole discussion begins. In 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. They were discussing flying saucers and whether extraterrestrial civilizations might exist. And Fermi asked a simple question: where is everybody? His point was this: the Milky Way galaxy is about 13 billion years old. It contains somewhere between 100 billion and 400 billion stars. Many of those stars have planets. We know this now from exoplanet surveys like Kepler and TESS. If even a tiny fraction of those planets developed intelligent life, and if even a small fraction of those civilizations developed space travel, the galaxy should be teeming with evidence of alien civilizations. They should have colonized the galaxy by now. They should have sent out probes. We should see their megastructures, their radio signals, their waste heat. We should see something, but we don't. We see nothing. The sky is silent. No signals, no visits, no artifacts, nothing. This is the Fermi paradox. If intelligent life should be common, why do we see no evidence of it? There are many proposed solutions to this paradox, hundreds of them actually. But I want to focus on one particular category of solutions, the one I find most compelling. Intelligent life is rare, vanishingly rare, maybe unique. Now this goes against the Copernican principle, the idea that Earth is not special, that we're a typical planet around a typical star. And for a long time, I believed in the Copernican principle. I thought intelligent life must be common, The universe is so vast, the number is so large, that intelligence must have arisen countless times. But the more I've learned, the more I've changed my mind. Let me walk you through the Drake equation, because it's a useful framework for thinking about this problem. In 1961, the astronomer Frank Drake proposed an equation to estimate the number of detectable civilizations in our galaxy. It looks like this. N equals R star times Fp times Ne times Fl times Fi times Fc times L. Let me break that down. N is the number of civilizations we might detect. R star is the rate of star formation in the galaxy. Fp is the fraction of stars with planets. Ne is the number of planets per star that could support life. Fl is the fraction of those planets where life actually develops. Fi is the fraction of life-bearing planets where intelligent life emerges. Fc is the fraction of intelligent civilizations that develop detectable technology. And L is the length of time such civilizations broadcast signals. Now, let's plug in some numbers. And this is where things get interesting and controversial. R star, the star formation rate, is about 1 to 3 stars per year in our galaxy. We know that pretty well. Fp, the fraction of stars with planets, is close to 1. Almost every star has planets. Kepler has shown us that. Ne, the number of habitable planets per star, is harder, but estimates range from 0.1 to 0.4. So roughly 10 to 40% of stars might have a planet in the habitable zone, the region where liquid water could exist. So far, the numbers look good. There should be billions of potentially habitable planets in our galaxy. But now we get to the really uncertain terms. Fl, the fraction of habitable planets where life actually develops. We have one data point, Earth. Life arose here about 3.8 billion years ago, relatively quickly after the planet formed. Does that mean life arises easily? Or did we get lucky? We don't know. Estimates for FL range from close to 1, almost every habitable planet develops life, down to 10 to the minus 10 or lower. 100 orders of magnitude of uncertainty. Then there's Fi, the fraction of life-bearing planets where intelligent life emerges. And this is where I think the real problem is. On Earth, life has existed for 3.8 billion years. For most of that time, about 3 billion years, life was nothing but single-celled organisms, bacteria and archaea. No multicellular life, no complexity, just single cells doing their thing. Then, about 600 million years ago, something extraordinary happened. The Cambrian explosion. Suddenly, geologically speaking, multicellular life appeared. Animals, complex body plans, eyes, nervous systems, predator-prey, relationships. The diversity of life exploded. Why did it take 3 billion years for this to happen? We don't really know, but it suggests that the transition from single-celled life to complex multicellular life is not easy, it's not inevitable. It requires special conditions that may be rare. Let me dig deeper into this, because the timeline is crucial for understanding just how improbable our existence is. For the first 2 billion years of life on Earth, from about 3.8 billion years ago to about 1.8 billion years ago, there wasn't even any oxygen in the atmosphere. Zero. The atmosphere was mostly nitrogen, carbon dioxide, and methane. The oceans were filled with single-celled organisms doing anaerobic metabolism. Then, around 2.4 billion years ago, something called the Great Oxidation Event occurred. Cyanobacteria, photosynthetic bacteria, had been producing oxygen as a waste product for hundreds of millions of years. At first, this oxygen was absorbed by iron dissolved in the oceans, forming rust that settled to the ocean floor. We can see these deposits today, banded iron formations, red layers in ancient rock. But eventually, all the iron in the oceans was oxidized, and the oxygen started accumulating in the atmosphere. This was catastrophic for most life at the time. Oxygen was toxic to the anaerobic organisms that dominated Earth. It was probably the first great mass extinction, but it also created an opportunity. Oxygen enables aerobic respiration, which is far more efficient than anaerobic metabolism. An aerobic organism can extract about 18 times more energy from glucose than an anaerobic one. This extra energy is what makes complex multicellular life possible. But even after oxygen appeared, it took another 1.8 billion years for complex life to emerge. Why? One problem was that oxygen levels fluctuated wildly. There was a period called the Boring Billion from about 1.8 billion to 0.8 billion years ago where oxygen levels were stuck at maybe 1 to 10% of modern levels, too low to support complex animals. It wasn't until around 800 million years ago that oxygen levels started rising again. And even then there was the snowball Earth period between about 720 and 635 million years ago when the entire planet froze over, possibly multiple times. Ice covered the oceans from pole to equator. Life barely survived. The Cambrian explosion, the sudden appearance of complex animals about 540 million years ago, happened only after all of these crises were resolved, after oxygen stabilized at high levels, after the planet thawed, after conditions became just right, and here's what disturbs me. There's no reason to think this sequence is inevitable. Oxygen production by cyanobacteria, the Great Oxidation Event, surviving the snowball Earth, these were contingent events. They could have failed to happen. Earth could have remained a planet of bacteria forever. And then, even after complex life emerged, it took another 600 million years for intelligent life, us, to appear. Think about that timeline. Out of 4.5 billion years of Earth's history, complex life has only existed for the last 600 million years, about 13% of the time. And intelligent, technological life has only existed for a few tens of thousands of years, about 0.0007% of Earth's history. For 99.99% of Earth's existence, there was no intelligence. No one to ask questions, no one to do science. Just bacteria, then eventually plants and animals, living and dying and evolving, but never thinking, never wondering, never knowing. Now, let me talk about the evolution of intelligence itself, because this is another massive bottleneck that most people don't appreciate. Intelligence is not an inevitable outcome of evolution. It's not even obviously advantageous in most ecological niches. Consider dinosaurs. They dominated Earth for about 165 million years, far longer than mammals have existed. And in all that time, with all those species, with all that evolutionary innovation, not one dinosaur species developed anything approaching human-level intelligence. Some dinosaurs had large brains relative to body size. Some were social. Some used tools in rudimentary ways. But none of them built cities, created language, or developed technology. Why not? Because intelligence is expensive. A human brain uses about 20% of the body's energy budget, despite being only 2% of body mass. That's an enormous metabolic cost. And for most of evolutionary history, that cost didn't pay off. Being a successful predator doesn't require intelligence. Sharks have been extremely successful for 450 million years with relatively small brains. Being a successful herbivore doesn't require intelligence. Grass has conquered huge swaths of the planet without a single neuron. Intelligence only becomes advantageous in very specific ecological niches, niches that reward problem solving, tool use, social cooperation, and long-term planning. On Earth, that niche was occupied by early hominids in Africa, savanna-dwelling primates who faced variable environments, needed to hunt cooperatively, and benefited from making tools and sharing knowledge. But that's one lineage, one group of species. Out of millions of lineages that have existed on Earth, only one, our lineage, developed high intelligence. Crows are intelligent, octopuses are intelligent, dolphins are intelligent, but none of them developed technology, none of them created civilization. And here's something even more sobering. Consciousness itself, subjective experience, the feeling of what it's like to be something we don't even know if it's necessary for intelligence. It's possible to imagine intelligent behavior without consciousness. Philosophical zombies, as they're called, entities that behave intelligently but have no inner experience. We don't know when consciousness emerged in evolutionary history. Did the first animals have it? Do insects have it? Do fish? We don't know. And we don't know if consciousness is a necessary prerequisite for the kind of intelligence that builds civilizations. All of this adds layers of improbability on top of improbability. Out of billions of species that have existed on Earth, only one has developed technology. Only one has built cities, written language, done science. One species out of billions. The biologist Ernst Mayr argued that this shows intelligence is not an evolutionary inevitability. Most species do perfectly fine without it. Intelligence is metabolically expensive. It requires a big brain, which requires a lot of energy. And for most of evolutionary history, intelligence wasn't particularly advantageous. Mayer's conclusion was that Fi is very small, maybe 10 to the minus 9 or smaller. If that's right, then even if every habitable planet develops life, intelligent life is still extraordinarily rare. Now, let me tell you about some recent work that makes the picture even bleaker. In 2024, two planetary scientists, Robert Stern and Taras Geria, published a paper proposing that the Drake equation is missing two crucial terms. They argue that plate tectonics and the presence of both continents and oceans are essential for intelligent life to develop. Plate tectonics, the slow movement of crustal plates on Earth's surface, does several important things. It recycles carbon between the atmosphere and the Earth's interior, regulating climate over geological timescales. It creates diverse environments, mountains, valleys, coastlines that drive evolution. It may have played a crucial role in the Cambrian explosion by increasing oxygen levels in the oceans. And crucially, plate tectonics requires specific conditions. A planet needs to be the right size, large enough to retain internal heat, but not so large that the crust becomes too thick to move. It needs liquid water to lubricate the plate boundaries. It probably needs a large moon to stabilize its rotation and create tides. Earth has all of these. But how many other planets do? Stern and Geria estimate that the fraction of habitable planets with significant continents, oceans, and long-lived plate tectonics is somewhere between 0.00003 and 0.002. That's tiny. Even at the high end, that's only 2 planets out of every 1,000 habitable planets. When you multiply this into the Drake equation, the number of expected civilizations in the galaxy drops dramatically. Instead of thousands or millions, you get numbers close to 0, maybe 1, maybe less than 1. Us. Alone. But let me add another layer to this problem that I find particularly troubling. Even if life exists elsewhere, even if it's common, detecting it is extraordinarily difficult. We've discovered over 5,000 exoplanets so far. We can measure their masses, their orbital periods, sometimes their atmospheric composition using transit spectroscopy. When the planet passes in front of its star, starlight filters through the atmosphere and we can see absorption lines from atmospheric gases. This technique works. We've detected water vapor, carbon dioxide, methane, even sodium in exoplanet atmospheres. And in principle, we could detect biosignatures, gases that indicate the presence of life. The most obvious biosignature would be oxygen combined with methane. On Earth, these gases coexist in our atmosphere in a state of chemical disequilibrium. Oxygen and methane react with each other, so the fact that both are present means something is constantly producing them. On Earth, that something is life. Plants produce oxygen through photosynthesis, and various microbes produce methane. Without life constantly replenishing these gases, they'd react away and disappear in less than 10 million years, an eye blink in geological time. So if we detect oxygen and methane together on an exoplanet, that's strong evidence for life. Not proof there are some abiotic processes that could produce these signatures, but strong evidence. But here's the problem. We haven't detected these signatures on any exoplanet yet. And the reason is, most exoplanets we've discovered are either too large, gas giants like Jupiter, or orbit too close to dim M-dwarf stars, which makes spectroscopy difficult. The James Webb Space Telescope, launched in 2021, has the capability to detect biosignatures on small, rocky exoplanets. We're finally reaching the point where we could detect life if it exists on nearby worlds. But we haven't, not yet. And the longer we look without finding anything, the more the silence becomes meaningful. Now, even if we detected biosignatures, even if we found oxygen and methane on a dozen nearby exoplanets, that would tell us life exists. But it wouldn't tell us intelligent life exists. For that, we need technosignatures, evidence of technology. And here the challenge becomes even more daunting. On Earth, human civilization has been producing detectable radio signals for less than 100 years. We started broadcasting radio in the 1920s, so our radio bubble, the expanding sphere of space where our signals could be detected, has a radius of only about 100 light years. The Milky Way is 100,000 light years across. Our radio bubble covers about 1/1,000,000th of the galaxy's volume. If another civilization exists in the Milky Way, and they're at our technological level, and they started broadcasting at the same time we did, the chances of our radio bubbles overlapping are minuscule. And that's assuming civilizations continue broadcasting for a long time. We're already shifting away from powerful broadcast radio toward fiber optics, satellite communication, and directed beams. Our planet is becoming radio quiet. In another 100 years, we might be essentially undetectable to SETI-type searches. If most civilizations go through a similar transition, a brief radio window lasting only a century or two, then even if the galaxy contains thousands of civilizations, we might never detect each other because our radio windows don't overlap. There's also the problem of what frequency to listen on. The electromagnetic spectrum is vast. We've searched a tiny fraction of it, at a tiny fraction of the sky, for a tiny fraction of the time. It's like scooping a cup of water from the ocean and concluding there are no fish because you didn't find any in your cup. But despite these challenges, I think the null result is significant. We've been looking for over 60 years. We've surveyed millions of stars. If intelligent life were common, if civilizations were everywhere, we should have found something by now. A stray signal, an anomaly, something. The silence suggests that either civilizations are rare, or they're quiet, or they don't last long, or they're doing something we're not imagining. Now, you might object. You might say, Lenny, you're making Earth-centric assumptions. Maybe life doesn't need plate tectonics. Maybe it doesn't need continents and oceans. Maybe silicon-based life in ammonia oceans on a tidally locked planet around an M-dwarf star could develop intelligence just fine. And you'd be right to push back on that. We only have one example of life, Earth life, and extrapolating from one data point is dangerous. But here's the thing. We have to work with what we know. And what we know is that on Earth, intelligence required billions of years of evolution, specific geological conditions, multiple extinction events that cleared ecological niches, and a lot of luck. Maybe there are other pathways. Maybe intelligence can emerge without all these conditions, but we have no evidence of that. And in the absence of evidence, I think it's more reasonable to assume that the conditions that led to us are necessary, or at least highly conducive. Let me talk about the Great Filter, because it's relevant here. The Great Filter is a concept proposed by Robin Hanson. The idea is that somewhere between the formation of a planet and the development of a galaxy-spanning civilization, there's a filter, a barrier that prevents most attempts at life from succeeding. The question is, where is the filter? Is it behind us or ahead of us? If the filter is behind us, if the hard step is going from non-life to life, or from simple life to complex life, then we've already passed it. We're past the hard part, and our future might be secure. But if the filter is ahead of us, if the hard step is surviving long enough to colonize the galaxy, then we're in trouble. Because it means most civilizations destroy themselves before they can expand beyond their home planet. Nuclear war, climate change, artificial intelligence gone wrong, pandemics, asteroid impacts, There are many ways a technological civilization could end. And here's what's disturbing. We have no evidence of civilizations that made it past the filter. The sky is silent. No one has colonized the galaxy. No one has left evidence of their existence that we can detect. That suggests that either the filter is behind us, meaning intelligent life is rare,
we
or the
cannot
filter
load
is
the
ahead
box.
of us,
We don't have
meaning
the
we're
address
doomed.
with us.
I'm hoping it's the former. I'm hoping we're just rare, not doomed. But the data doesn't let us distinguish between these possibilities yet. Now, let me address the argument from large numbers, because I hear this all the time. Lenny, the universe is so big, there are so many stars, so many planets. Even if the odds of intelligent life are tiny, there should still be lots of civilizations out there. The numbers are just too large. And I used to find this argument compelling, but I don't anymore. Here's why. Even if the universe is vast, the probabilities can be even vaster. If the probability of intelligent life arising on any given habitable planet is 10 to the minus 21 in 100 billion, then even with billions of habitable planets, you'd expect fewer than one intelligent civilization in the galaxy. And we have no way of knowing if 10 to the minus 20 is too pessimistic or too optimistic. It could be 10 to the minus 50, it could be 10 to the minus 100. The point is, large numbers don't help if the probabilities are small enough. Let me give you an analogy. Imagine you're trying to win the lottery. The odds of winning are 1 in 300 million. Now, you buy 1 billion tickets. Your odds improve, sure, but you're still unlikely to win. That's the situation with intelligent life. Yes, there are billions of planets, but if the odds of any one planet developing intelligence are tiny enough, those billions don't matter. Now, here's where this connects to my own work on the string landscape and the anthropic principle, and I think this perspective is crucial for understanding our place in the universe. In the multiverse picture, I've defended eternal inflation populating the string landscape. There are an incomprehensibly large number of universes, maybe 10 to the 500 different vacuum states, each realized infinitely many times in different pocket universes. Most of those universes are sterile, dead, unsuitable for life because the constants of nature are wrong. The cosmological constant is too large, or electrons are too heavy, or carbon can't form, or chemistry doesn't work. We exist in one of the rare universes where conditions allow for life. That's observer selection. We couldn't exist in any other kind of universe. So we necessarily find ourselves in a life-permitting universe. But here's the key question. Within our particular universe, with our particular laws of physics and constants of nature, how common is life? How common is intelligence? The multiverse explains why our universe has the right laws, but it doesn't guarantee that intelligent life is common within our universe. It's possible, maybe even likely, that even in a life-permitting universe like ours, the actual emergence of intelligent life is so improbable, so contingent on specific conditions and chance events, that it happens only once per universe, or once per galaxy, or once per observable universe. The anthropic principle explains why we exist, but it doesn't explain why there should be lots of us. This is sometimes called the weak anthropic principle versus the strong anthropic principle. The weak version just says we exist in a universe compatible with our existence. The strong version says the universe must produce observers like us. I believe in the weak version. I'm skeptical of the strong version. And if I'm right, then the fact that we exist, that Earth has intelligent life, doesn't imply that intelligent life is common. It just implies that it happened at least once here. Think about the lottery analogy again. If you win the lottery, that doesn't mean lots of other people won too. It just means someone won, you. We won the cosmic lottery. We exist in a life-permitting universe on a planet with the right geology, with the right history of oxygen accumulation and mass extinctions and evolutionary contingencies, in the right galaxy at the right time. That doesn't mean there are lots of other winners. It might just mean we got lucky. And this brings me to something I find both beautiful and terrifying. The observer selection effect might be masking our uniqueness. If intelligent life is incredibly rare, maybe unique in the observable universe, we would still expect to find ourselves in exactly the situation we observe. We would find ourselves on a habitable planet in a life-permitting universe surrounded by a vast cosmos that appears empty, because that's the only kind of place observers can exist. The universe could contain 1 million intelligent civilizations, or it could contain just one, and from our perspective we couldn't tell the difference. We would observe the same thing either way ourselves, apparently alone, wondering if anyone else is out there. This is deeply unsettling to me. It means the data we have our own existence, the silence of the cosmos, is compatible with both life is common and we are unique. We can't distinguish between these hypotheses observationally, at least not yet. All we can do is make estimates based on what we know about biology, geology, and the history of life on Earth. And those estimates, as I've argued, suggest that intelligent life is rare. Now, there's one more thing I want to talk about, the temporal aspect. The universe is about 13.8 billion years old. Our sun and solar system formed about 4.6 billion years ago. Earth is about 4.5 billion years old. We're relatively early. There are stars that formed billions of years before our sun day. There could have been civilizations that arose billions of years ago. And if they arose billions of years ago, and if they developed space travel, they've had billions of years to colonize the galaxy. The galaxy should be completely filled with their descendants. But it's not. At least we see no evidence that it is. This is sometimes called the Hart-Tipler argument. Michael Hart and Frank Tipler independently argued that the absence of aliens on Earth proves that no extraterrestrial civilizations exist. Because if they existed, they would have colonized the galaxy by now, including Earth. Now, there are counter-arguments. Maybe civilizations don't colonize. Maybe they prefer to stay home. Maybe they're here but hiding. Maybe they visited in the past and we miss them. But all of these require special explanations. They require assuming that every civilization behaves in a particular way. That seems implausible. The simpler explanation Occam's razor is that there are no civilizations to colonize the galaxy because intelligent life is rare, maybe unique. But let me add some nuance to the temporal argument, because the timing might be more subtle than it first appears. The first stars in the universe, population 3 stars, formed only a few 100 million years after the Big Bang. But these stars were made purely of hydrogen and helium. No heavy elements, no carbon, no oxygen, no silicon, no iron. Nothing heavier than helium. You can't make planets out of hydrogen and helium. You can't make rocks. You can't make chemistry. You can't make life. Heavy elements, elements heavier than helium, are made inside stars through nuclear fusion and then distributed through space when stars explode as supernovae. This process is called stellar nucleosynthesis. But it takes time. Multiple generations of stars have to live and die before enough heavy elements accumulate to form rocky planets. The first rocky planets probably couldn't have formed until the universe was several billion years old. Maybe not until 6 or 7 billion years after the Big Bang. And even then, conditions might not have been ideal. The early universe was more violent, supernova rates were higher, gamma ray bursts were more common, radiation levels were higher. It's possible that the galactic habitable zone, the region of the galaxy where conditions are suitable for life, was much smaller in the early universe than it is now, maybe non-existent. So even though the universe is 13.8 billion years old, the window for intelligent life might only have opened in the last few billion years. If that's true, then we're not mysteriously late. We're actually relatively early. We might be among the first civilizations in the galaxy, possibly even the first. And if that's the case, then the silence makes sense. There are no ancient civilizations because there hasn't been enough time for them to arise. We're pioneers, first explorers. The first eyes the universe has opened to look at itself. That's a beautiful thought. But it doesn't solve the Fermi paradox completely, because even if we're early, there should still be some civilizations arising around the same time as us. Stars similar to the Sun, planets similar to Earth, forming at similar times. Where are they? Unless, and this is the possibility I keep coming back to, The barriers are so high, the filters so severe, that intelligent life really is incredibly rare. Maybe one civilization per galaxy, maybe one per 100 galaxies, maybe fewer, in which case we might be alone for a very long time, maybe forever. You know, when I was younger, I was optimistic about SETI, the search for extraterrestrial intelligence. I thought we'd find signals. I thought we'd make contact. I thought the universe must be full of intelligent life. But we've been listening for over 60 years now. We've surveyed millions of stars. We've looked at thousands of exoplanets. We've monitored the sky for radio signals, optical signals, infrared signatures, and we've found nothing. Absolutely nothing. No technosignatures, no evidence of megastructures, no directed signals, no accidental leakage, nothing. The silence is deafening. And at some point, you have to take that seriously. At some point, absence of evidence becomes evidence of absence. I'm not saying we should stop looking. I'm not saying SETI is a waste of time. We should absolutely keep searching, keep listening, keep looking. But I think we need to be prepared for the possibility, the likelihood, even that we're alone. That intelligent life is so rare, so contingent, so improbable, that it may have arisen only once in the observable universe. Us. And if that's true, if we really are alone, then we have an enormous responsibility. We're the only ones who can ask questions about the universe, who can do science, who can appreciate beauty, who can create art and music and literature. We're the universe's way of understanding itself. And if we destroy ourselves through war, through environmental collapse, through our own stupidity, then that light goes out forever, or at least for billions of years. That's a heavy burden. But it's also inspiring in a way. It means we matter. What we do matters. The choices we make matter. If we're the only intelligence in the galaxy, maybe in the universe, then preserving our civilization, expanding into space, ensuring our long-term survival becomes not just a human imperative, but a cosmic one. Let me end with this. I could be wrong. I hope I'm wrong. I would love to be proven wrong by the discovery of an alien signal tomorrow. But based on everything we know, based on the Drake equation, based on the geological requirements for complex life, based on the improbability of intelligence, based on the silence of the cosmos, I think intelligent life is unlikely, vanishingly unlikely. We might be the only ones. And that means we need to take care of ourselves, take care of our planet, and take care of our future. Because if we're the universe's only shot at intelligence, then we can't afford to fail. Thank you for listening. Look up at the stars tonight. And remember, we might be the only ones looking back.
The physics
Let me tell you something
that makes interstellar travel impossible.
that Hollywood doesn't want you to know. Something that science fiction writers ignore. Something that optimistic futurists dismiss as mere engineering challenges. Interstellar travel, sending humans to other star systems, is not just difficult. It's not just expensive. It's not just beyond our current technology. It's impossible. Fundamentally, physically impossible. I don't mean impossible in the sense that people once thought heavier-than-air flight was impossible, or that they thought we'd never reach the moon. I mean impossible in the sense that perpetual motion machines are impossible, in the sense that traveling faster than light is impossible, in the sense that the laws of physics themselves forbid it. After 50 years of thinking about physics, of working on relativity and quantum mechanics and cosmology, I've come to accept a hard truth. We are stuck here, on Earth, in our solar system, maybe eventually spreading throughout the Oort cloud, but the stars, the thousands of potentially habitable exoplanets we've discovered, they might as well be in different universes. Let me show you why, and I'm going to be precise about this. No hand-waving, no appeals to future technology we can't imagine, just physics. Hard, cold, unforgiving physics. The fundamental problems are distance, energy, time, and biology. Each one alone is nearly insurmountable. Together, they form an absolute barrier. Let's start with distance, the problem of distance. The nearest star system to Earth is Alpha Centauri, about 4.37 light years away. That's roughly 41 trillion kilometers. To put this in perspective, if Earth were the size of a grain of sand, Alpha Centauri would be 40 kilometers away. Voyager 1, our fastest spacecraft, is traveling at about 17 kilometers per second relative to the Sunday. At that speed, it would take about 75,000 years to reach Alpha Centauri. That's not a typo. 75,000 years, longer than all of recorded human history. And Alpha Centauri is the closest star. The average distance between stars in our galaxy is about 5 light years. Most interesting exoplanets we've found are hundreds or thousands of light years away. Kepler 186f, one of the most Earth-like exoplanets discovered, is 500 light years distant. At Voyager's speed, reaching it would take more than 8 million years. Now, you might say, well, we just need to go faster. And yes, that's obviously true. But here's where the physics gets brutal. Let's imagine we want to make the trip to Alpha Centauri in a human lifetime, say, 50 years. That means we need to travel at about 10% the speed of light. That's 30,000 kilometers per second, about 1,800 times faster than Voyager. Can we do that? Let's look at the energy requirements. The energy problem. The kinetic energy of a moving object is 1/2 mass times velocity squared. At low speeds, this is manageable. But at 10% the speed of light, you need to use the relativistic formula, which is even worse. Let's be conservative and assume we're sending a small spacecraft, say 1,000 kilograms. That's tiny, barely enough for one person and minimal life support. No fuel, because we'll calculate that separately. The kinetic energy needed to accelerate this 1,000 kilogram spacecraft to 10% light speed is about 4.5 times 10 to the 17th joules. That's 450 petajoules. How much energy is that? The entire world's energy consumption in 2023 was about 600 exajoules. That's 600 times 10 to the 18th joules per year. So accelerating our tiny spacecraft would consume about 1/10,000th of a year's worth of all human energy production. That's the energy output of all human civilization, every power plant, every car, every light bulb running for about 50 minutes, just to accelerate the spacecraft. You still need to slow it down when you arrive, which takes the same energy again, so double that. An hour and 40 minutes of all human energy production for a 1,000 kilogram spacecraft. A payload smaller than a compact car. Now let's talk about the fuel. If you're using chemical rockets, the best we have, the energy density is pathetic. Gasoline contains about 46 megajoules per kilogram. Even hydrogen-oxygen rockets, which are better, give you about 13 megajoules per kilogram. To get 450 petajoules from chemical fuel, you'd need about 35 billion kilograms of fuel. That's 35 million metric tons. For comparison, the International Space Station has a mass of about 450 metric tons. Your fuel alone would be 75,000 times more massive than the ISS. And remember the rocket equation. The more fuel you carry, the more mass you have to accelerate, which means you need more fuel, which means more mass, in an exponential spiral. When you do the calculation properly using the Tsiolkovsky rocket equation, you find that chemical rockets simply cannot reach 10% light speed. The fuel-to-payload ratio becomes astronomical. You'd need a fuel mass many times greater than the mass of the observable universe. So chemical rockets are out. What about nuclear propulsion? Nuclear fission releases about 80 trillion joules per kilogram of uranium. 235. That's about 1,000,000 times better than chemical fuel. Nuclear fusion, if we could make it work, efficiently releases about 600 trillion joules per kilogram of fuel. Let's use fusion, since we're being optimistic. To get 450 petajoules, you'd need about 750 kilograms of fusion fuel. That's actually manageable. Add another 750 kilograms for deceleration, and you're at 1,000 2,500 kilograms of fuel. So the total mass of your spacecraft payload plus fuel would be 2,500 kilograms. Much better. But there's a problem. Converting fusion energy into directed thrust is hard. Really hard. Current fusion reactor designs, like ITER, are massive and inefficient. They require huge magnetic coils, cooling systems, and structural support. The reactor mass dwarfs the fuel mass. Even if we imagine a breakthrough in fusion propulsion, a lightweight, efficient reactor, we face another problem. You're not just accelerating fuel. You're accelerating the engine, the structure, the radiation shielding, the payload. Every kilogram of additional mass requires more fuel. And speaking of radiation shielding, a fusion rocket creates intense neutron radiation. The crew compartment needs heavy shielding. Water, lead, polyethylene all add mass. Kilograms of shielding for every kilogram of payload. When you account for all of this realistically, the mass ratios become prohibitive again. We're back to needing many times the payload mass in fuel and structure. But let's keep being optimistic. Let's imagine we solve all of this. Let's assume perfect fusion drives with nearly 100% efficiency and minimal mass overhead. Can we finally make the journey? Not quite, because there's another energy problem. Interstellar dust. The dust problem. Space is not empty. Even the near vacuum of interstellar space contains about 1 atom per cubic centimeter, mostly hydrogen. At low speeds, this is negligible. But at 10% the speed of light, you're hitting about 3 times 10 to the 13th hydrogen atoms per square meter per second. Each collision transfers energy. At 10% light speed, each hydrogen atom hits with a kinetic energy of about 5 kiloelectron volts. That doesn't sound like much, but multiply by trillions of atoms per second hitting every square meter of your spacecraft's cross-section. For a spacecraft with a frontal area of just 10 square meters, very small, you're absorbing about 2.4 megawatts of power continuously.
Looks like as if a pilot
That's like
is
having
approaching.
2,401 kilowatt heaters running constantly on the front of your ship. This energy turns into heat, it ablates the hull, it creates secondary radiation, you need shielding which adds mass, which requires more fuel, which makes the problem worse, and hydrogen atoms are the least of your worries. There are also dust grains, tiny particles, mostly carbon and silicates, averaging about a micrometer in size. There's roughly 1 such grain per 1,000 cubic kilometers. At 10% light speed, a 1 microgram dust grain hits with the kinetic energy of about 45,000 joules. That's equivalent to 10 grams of TNT. Every grain punches a hole through your spacecraft like a hypervelocity bullet. Over a 50-year journey, your spacecraft will sweep through a volume of about 20 trillion cubic kilometers. That's 20 billion potential impacts. Even with the sparse distribution, you're looking at millions of grain impacts. You need shielding, heavy shielding, or a massive magnetic field to deflect charged particles. Both add mass, both require energy, both make the mission harder. We're accumulating problems, but it gets worse. The time problem. Even if we could somehow solve the energy and shielding problems, even if we had magical propulsion systems that violate everything we know about engineering, we face the problem of time. A 50-year journey to Alpha Centauri means 50 years on the spacecraft. But who's going to sign up for a one-way 50-year journey to a star system we've barely studied? You might think, well, we'll put people in suspended animation or cryogenic sleep. This is not technology. This is fantasy. We cannot freeze and revive humans. Every cell in your body contains water, and water expands when it freezes, rupturing cell membranes. The damage is catastrophic and irreversible. Some researchers are working on inducing hibernation-like states through metabolic suppression. Maybe, and this is a big maybe, we could slow metabolism by a factor of 10. That would make a 50-year journey feel like 5 years to the crew. Still half a decade of their lives spent in a tiny spacecraft. And here's the darker problem. What happens on Earth during those 50 years? Technology advances. If we can barely send a spacecraft at 10% light speed in, say, the year 2100, what will be possible by 2150? Probably 20% light speed, or 30%. So you launch your crew in 2100, they arrive at Alpha Centauri in 2150, but a faster ship launched in 2125 arrives in 2140. Your crew spent 50 years traveling to a destination that was already reached by others who left later. This is called the weight calculation, and it creates a perverse incentive. It's always better to wait for better technology than to launch with current technology. Unless you know your technology is close to the theoretical limits, which brings us back to the speed of light, and that's the ultimate time problem, relativity. The relativity barrier. Let's say we want to make interstellar travel reasonable, a few years of trip time subjectively for the crew. To do this, we need to approach the speed of light closely, say 90% of light speed. At 90% light speed, time dilation becomes significant. Gamma factor is about 2.3. This means for every year that passes on the spacecraft, about 2.3 years pass on Earth. A trip to Alpha Centauri at 90% light speed would take about 4.9 years Earth time. But due to time dilation, the crew would experience only about 1 years. That's manageable, but the energy requirements become insane. The relativistic kinetic energy of a 1,000 kilogram spacecraft at 90% light speed is about 5.8 times 10 to the 19th joules. That's 58 exajoules. Almost 10% of annual global energy production for a 1,000 kilogram payload. To accelerate 1,000 kilograms to 90% light speed using fusion fuel at 100% conversion efficiency, you'd need about 96,000 kilograms of fuel. 96 tons of fuel for every ton of payload. And the radiation problem gets worse. Those hydrogen atoms, at 90% light speed, each one hits with about 430 kilo electron volts. Your spacecraft is now absorbing about 200 megawatts of power from interstellar hydrogen collisions. That's the output of a small nuclear power plant concentrated on the front surface of your ship. The dust grains become relativistic missiles. A 1 microgram grain at 90% light speed hits with 5.8 million joules. That's more than a kilogram of TNT. Each grain impact is an explosion. You'd need shielding meters thick, made of the densest materials, adding thousands of kilograms of mass, requiring millions of kilograms of fuel. And we haven't even talked about what happens when you want to stop. The deceleration problem. You've accelerated to 90% light speed. You've somehow survived the radiation and dust impacts. You're approaching Alpha Centauri. Now you need to slow down. If you don't slow down, you'll zip through the system at 270,000 kilometers per second. The entire star system will flash by in hours. You won't be able to orbit, you won't be able to land. You'll just keep going into the void. So you need to decelerate, which requires the same energy you use to accelerate. Another 58 exajoules, another 96 tons of fuel per ton of payload. But here's the problem. You had to carry that deceleration fuel with you the entire journey, which means you had to accelerate it at the beginning, which means you needed more fuel to accelerate the fuel you need to decelerate. The rocket equation strikes again. When you do the math, the fuel requirements spiral to absurdity. You need thousands of tons of fuel to carry hundreds of tons of fuel to slow down a spacecraft, carrying tens of tons of fuel to slow down a spacecraft with 1 ton of payload. Some proposals suggest using magnetic scoops to collect interstellar hydrogen during the journey and use it as fuel. The Bussard ramjet, proposed in 1960. Beautiful idea, doesn't work. The problem, the drag from collecting the hydrogen creates more deceleration than you gain from burning it. You actually slow down, the numbers don't work out. Robert Zubrin and Dana Andrews proved this in the 1990s. Other proposals. Laser sail, pushed by Earth-based lasers for acceleration, then deploy a magnetic sail for deceleration using the star's stellar wind. Clever, but the engineering is fantastical. You need lasers with petawatt power levels. You need sails thousands of kilometers across. You need perfect stability and control over light-year distances. We're leaving physics and entering fantasy. The biology problem. Let's pretend, for the sake of argument, that we solve all the physics and engineering problems. We have a spacecraft that can reach Alpha Centauri in a few years, ship time. Can we actually send humans? No. Because biology, cosmic radiation is the killer. Outside Earth's protective magnetic field and atmosphere, you're exposed to galactic cosmic rays and solar energetic particles. These are high-energy protons and heavy ions that pass through spacecraft walls like they're not there. On the International Space Station, astronauts receive about 150 millisieverts of radiation per year. That's about 50 times more than you'd receive on Earth's surface. For a 6-month mission, this is acceptable. It increases cancer risk slightly, but remains within safety guidelines. But an interstellar journey, even a short one of 5 years, you're looking at 750 millisieverts minimum. Probably much more, since you're traveling through interstellar space far from the sun's heliosphere, which provides some shielding. At these doses, you're significantly increasing cancer risk. Cataracts become likely, radiation sickness is possible, and we don't fully understand the long-term neurological effects of cosmic ray exposure to the brain. The only way to shield against cosmic rays is mass. Meters of water, lead, or polyethylene, thousands of kilograms per person, which we're back to the mass problem, the fuel problem, the energy problem, and cosmic rays are just one issue. There's also bone density loss in microgravity, about 1 to 2% per month. After a year, astronauts have osteoporosis level bone density. We can mitigate this with exercise, but not eliminate it. Muscle atrophy. Even with rigorous exercise, astronauts lose 20 to 30% of muscle mass on long missions. Vision problems. Many astronauts develop vision changes due to fluid shifts in microgravity. The mechanism isn't fully understood. Immune system suppression. Extended spaceflight weakens immune function, making infections more dangerous. Psychological issues. Isolation, confinement, monotony, distance from Earth all take psychological tolls. ISS astronauts are in constant contact with Earth and can return in hours if needed. An interstellar crew would be years from home with no possibility of rescue. Some of these problems could be solved with rotating spacecraft to create artificial gravity, but rotation adds engineering complexity. It adds mass. It requires structural strength. The rotating section needs to be large, at least 100 meters radius, to avoid disorienting Coriolis effects. We're back to the mass problem, the energy problem, the impossibility, generational ships. Maybe you think we don't send people for a few years, we send them for generations. A generation ship, a massive habitat carrying thousands of people who will live, reproduce, and die during the centuries-long journey. This is not physics anymore. This is sociology, ecology, genetics, and psychology. And the problems are staggering. You need a closed-loop life support system. Perfect recycling of air, water, and nutrients for centuries. We cannot do this. Our best closed system experiments, Biosphere 2, for example, failed to maintain balance even for years. You need genetic diversity. A founding population of at least several hundred people to avoid inbreeding, probably thousands for long-term viability. You need social stability. Your ship is a dictatorship. There's nowhere to escape if society breaks down. How do you maintain order, culture, purpose across generations of people who never chose to be there? You need redundancy in critical systems. If the water recycling fails, everyone dies. If the power system fails, everyone dies. You need backups, spares, repair capabilities for systems we barely understand for centuries without resupply. The mass of such a ship would be millions of tons. The energy to accelerate it would be, I don't even want to calculate it, a significant fraction of all the energy humans have ever produced. And for what? To send a few thousand people to a star system decades or centuries away, where they'll arrive as technological primitives compared to whatever Earth has developed in the meantime. Assuming Earth hasn't collapsed, or humanity hasn't gone extinct, or we haven't discovered faster than light travel, spoiler, we won't, that's even more impossible. Generation ship's a fantasy, appealing fantasy for science fiction, but fantasy nonetheless. Alternative destinations, you might argue, okay, interstellar travel is impossible for humans, but what about probes, small robots? Yes. This is much more plausible. The mass is lower, the energy requirements are manageable, and robots don't care about radiation or time. The Breakthrough Starshot project proposes exactly this. Centimeter-scale spacecraft with light sails, accelerated to 20% light speed by ground-based lasers. Trip time to Alpha Centauri, about 20 years. The physics works, barely. The engineering is extraordinarily challenging, but not impossible. The energy requirements are huge, but conceivably achievable with globally coordinated effort. But these are probes, not colonization, not human expansion. They'd send back pictures, data, measurements. Wonderful for science, useless for establishing a presence. And they're one way. At 20% light speed, there's no slowing down. They flash through the Alpha Centauri system in days, cameras clicking, then they're gone forever into the void. Or you might argue, what about the solar system? Mars? The moons of Jupiter and Saturn? Yes, these are reachable, difficult, expensive, requiring centuries of technology development, but not impossible. Mars is 7 months away, the moons of Jupiter, a few years. Even the outer solar system is reachable within decades. We could plausibly establish permanent settlements on Mars, underground habitats on the moon, mining operations in the asteroid belt, research stations on Titan or Europa. But this is not interstellar travel, this is staying home. Alpha Centauri might as well be in another dimension for all the good it does us. The Fermi paradox solution. Here's what I think the physics of interstellar travel tells us about the Fermi paradox. Enrico Fermi famously asked, where is everybody? If intelligent life is common, why don't we see evidence of other civilizations? Many solutions have been proposed. Maybe life is rare. Maybe intelligence is rare. Maybe civilizations destroy themselves. Maybe they're hiding. Maybe they're here and we don't recognize them. But there's a simpler answer. Interstellar colonization is impossible. Every civilization that evolves, regardless of how technologically advanced they become, hits the same wall we're hitting. The physics is universal. Energy requirements scale the same way. The speed of light is the same everywhere. So civilizations arise, they spread through their solar systems, and then they stop because the stars are too far away, too expensive to reach, too dangerous to travel to. We're alone not because we're special or first or doomed. We're alone because everyone is alone, trapped in their own solar systems by the tyranny of distance and the conservation of energy. This is the solution to the Fermi paradox that physics suggests, and it's probably correct. The philosophical implications, what does it mean if we're truly stuck here, if the stars are unreachable, not just now, but forever? It means Earth and our solar system are all we get. This is it. This is humanity's domain. About 10 to the 13th cubic kilometers of usable space, if we're generous, and include the entire volume of the solar system out to the Kuiper belt. It means the exoplanets we're discovering, the Earth-like worlds orbiting other stars, are forever beyond our reach. We can look, we can measure, we can dream, but we can never go there. They're dead to us. It means the long-term future of humanity is tied entirely to the sun's lifespan and the resources of our solar system. We have about 1 billion years before the sun's luminosity increases enough to make Earth uninhabitable. Maybe 5 billion years before the sun becomes a red giant and swallows the inner planets. That's a long time. Plenty of time for humanity to flourish, evolve, transform into something unrecognizable. But it's finite, and it's local. It also means we need to be more careful with what we have. If Earth is not just our home, but our only possible home, if there's no backup planet we can flee to, if we destroy this one, then preservation becomes paramount. climate change, nuclear war, ecosystem collapse, artificial intelligence, risks. These aren't just threats to our current civilization. They're threats to the only civilization that can ever exist in this corner of the galaxy. Some people find this depressing. I find it clarifying. It focuses the mind on what matters. We have one planet, one solar system, one chance. We should make the most of it. Could I be wrong? Let me address the obvious question. Could I be wrong about interstellar travel being impossible? Of course. I've been wrong before. Every physicist has. The history of science is full of confident pronouncements that turned out to be false. Lord Kelvin said heavier-than-air flight was impossible. Nuclear physicist Ernest Rutherford said extracting energy from atoms was moonshine. Astronomer Royal Richard Woolley said space travel was utter bilge. They were all wrong, so maybe I'm wrong too. But here's the difference. Those predictions were based on limited understanding or imagination failures. They didn't account for new physics or engineering breakthroughs. My argument is based on fundamental limits. The speed of light is not a technological limitation. It's a feature of space-time itself. Energy conservation is not an engineering challenge. It's a law of nature. The distances between stars are not a temporary obstacle. They're a geometric fact about the universe we inhabit. Could there be loopholes? Could we discover new physics that allows faster-than-light travel? Wormholes? Warp drives? Exotic matter with negative energy density? These appear in general relativity's equations as mathematical possibilities, but they require things we've never observed and have good theoretical reasons to think don't exist. Wormholes require exotic matter with negative energy density in quantities that exceed anything quantum field theory allows. Warp drives require similar exotica, plus the ability to manipulate space-time curvature on macroscopic scales with energies exceeding the mass energy of planets. These are not engineering challenges. They're demands for physics that violates everything we know. Could we be missing something fundamental? Sure. Maybe quantum gravity will reveal new possibilities. Maybe there are extra dimensions we can shortcut through. Maybe consciousness can transcend space in ways we don't understand. But betting on unknown physics to save us from known physics is not rational. It's wishful thinking. The smart money says, interstellar travel is impossible. Act accordingly. Conclusion. I know this is not what you wanted to hear. Science fiction has trained us to expect Star Trek, Star Wars, galaxies full of civilizations, trading and warring and exploring. But science fiction is fiction. Physics is reality. And physics says the stars are too far away, the energy requirements too extreme, the dangers too great, the timescales too long. We are islanders in a vast ocean. We can see other islands on the horizon, those exoplanets orbiting distant stars. We can study them with telescopes. We can wonder what's there, but we can never visit them. Our island, the solar system, is large enough for a very long future. We can build habitats throughout it. We can use the sun's energy for billions of years. We can create a rich, complex, enduring civilization. But we'll do it here, alone, without ever touching another world that orbits another star. That's what physics tells me. And after 50 years of listening to what physics says, I've learned to trust it. The universe is beautiful and vast and full of wonders, but most of those wonders are beyond our reach, and we need to accept that. We're home. We've always been home, and we always will be.
Don't know if that ace still around here. To see a player in the dark is a little bit different. But it looks like as if he at least made it out of his ship.
Laying down covering fire.
Oh! That was the wrong one. Shit.
We lost one. Got you covered.
They look up. Yeah.
Someone just got
He
blasted.
was on the tower. He had to be on the tower, yes.
Ah, god damn it!
Unfortunately, our respawn